Okay. Mm-hmm. So today's my talk is around our Chandra X-ray observations of the Akari NEP deep field, and there is some deviation from my abstract, so I'm sorry for that. So the scope of my talk is about the Chandra observation of the Akari NEP field. First, a brief introduction, and then I'll move on to the one Compton thick object that we found in our basically the Keck spectroscopy and Akari data, Chandra data with all other multi-wavelengths data. And then I'll briefly talk about the work on progress on trying to find the counterparts of X-ray sources in Subaru, HSC, and CFE-HT will come. And I'll summarize it. So this is basically the color-coded image of our Chandra observation, color-coded by energy. And so our basic parameters are like it's the modest Chandra survey of 0.25 square degrees, total of about 300 kiloseconds, including our data and archive. And the typical exposure is between 40 and 80 kiloseconds. And this shade is the exposure map. And this red square is the older Subaru Supreme Cam field of view superimposed on the 15-micron Akari image of the Akari NEP deep field. And the Krumpe et al. 2015 actually listed 457 X-ray point sources. Okay, then now the motivation of this particular Chandra observation was like that. Actually, we have the entire multi-wavelength data from UV, including Akari and Herschel, and by the SED fit, we can get the infrared luminosity contributed by AGN, and this horizontal axis, and vertical axis is the X-ray luminosity without correcting for any absorption. And this dotted line represent the kind of empirical relation in unabsorbed AGNs, including these triangles are optically confirmed type 1 AGN. And since the infrared light is less affected by absorption than X-ray, then if you have absorption, you go down in this particular figure. And these lines, it's redshift dependent, indicates the border at the column density of 10 to 24 per square centimeter. So everything below this line are strong candidates for Compton thick AGNs. And that's all the analysis. And now that our postdoc, Martin Herrera and Doki, has been re-investigating with that. And in the infrared side, he actually made the module for the Nenkova-Clumpy model for Seagull, and he got this infrared AGN luminosity. And then there are more spectroscopic redshifts available. Then this is what we get right now. And we have a little bit lower lower X-ray luminosity at the high luminosity ends, but still we have to see because this may be some kind of Eddington bias. And actually, if you have a closer but more and more luminous AGNs in the Akari NEP wide field, and if you combine it with E Rosetta, you can probe this particular part more precisely. So the next topic is about this particular component AGN ANEP-D CXO245. And actually, this came from our telecom where the group by Matsuura-san at Kwansei Gakuin University went over the entire Keck spectra of the ANEP-D field and found this particular object where the narrow line region lines have double peaked, separated by 500 kilometers per second. And then we kind of have a discussion what's going on, whether it's a bipolar outflow, reflects a bipolar outflow, or like it may be a kind of a rotating ring. And if you get here some geometry or like viewing angle and the torus opening angle information, that could be give a clue. Now, I often look at like a Chandra spectrum, and that's what I get. And we have a very strong ion line right here. And that is really typical of a quantum-thick AGN. So I applied I made the X-ray spectral analysis using the module named Exoclumpy by Tanimoto et al. At Kyoto, then at Kyoto University. And then this is basically designed to have the same geometry and the parameters as the Nenkova-Clumpy model. And this is a constraint that we get. And the particular interesting is this particular constraint in the geometry of viewing angle and the, say, torus height. And still like this is a kind of loose constraint. Another important thing is that the equatorial column density of 10 to the 24.7. So we are sure that it's bona fide quantum-thick AGN. And we get the rather high intrinsic X-ray luminosity. Now, we collected the entire suite of photometries from this object using the Akari NEP data, and then applied the, with all other components, we applied the Nenkova 2008 Clumpy model as a SIGAL module. And then this is the kind of constraint we get. And then we do more because actually each of them are analyzed separately, but we can just combine infrared and X-ray constraint. And this is a kind of the constraint that we get. Constraints are still poor to give any clue of the origin of the double peak, but at least we tried and we showed the methods. Okay. Now, the final topic is the constructing the identification catalog. That's work in progress. Actually, we started doing it with the Supreme Cam data, but we basically waited for the high-pass Supreme Cam data to complete this work. So we have X-ray positional error, and for each X-ray source, we listed the candidates up to 3 sigma. And first, we basically looked for candidates in the high-pass Supreme Cam G band as a base catalog. And if we had problem, then we just looked into CFHT KS catalog. And but before doing that, we identified special cases like a bright saturated stars, or some of the X-ray sources are from a cluster diffuse X-ray emission falsely cataloged as multiple X-ray point sources, and we excluded this. Then if there are multiple G-band candidates for an X-ray source, we use the something called likelihood ratio technique. And here are some examples. of the identification process. This is X-ray image, HSC green band will come K band. And we have blue ones are like kind of 3 sigma error circle of the X-ray source position. And green plus is the HSC cataloged object. And we just put the KS in purple only if there is no counterpart in G. And this is a simple case, just one object, one-to-one corresponding. But if you have a larger error bar, then there are 4 G band sources there. In this case, we just calculate the probability of each one is a true counterpart by the likelihood ratio, as I explained in the next slide. And then this is a kind of a little bit tricky because we have G band source, 3 G band sources. At the center, I don't see any in the G band. But if you look at K band at the center, basically this seems to be the true counterpart. So so we have to basically think of these things a little bit more individually. And another tricky case is that in the G band, it's saturated. It's a bright star. But in the catalog, there are 4 actually objects in the G band catalog. But in the KS band, it's saturated and it gives the right position. So there are some complicated cases. Okay, then I'll just briefly explain about this likelihood ratio techniques and the our new method. And this is a likelihood ratio. Basically, is the QM is the optical magnitude distribution of X-ray sources normalized. FR is a kind of the positional error in X-ray source. NM is the like a number density of the optical counterpart. Now, what we do, this is traditionally, this QM is for just for X-ray sources without considering any flux, but we are doing in a flux-dependent manner. So work in progress, so stay tuned. So this is my summary. We continue our studies using our Chandra data on Akari NEP-D field with updated ancillary data sets and improved methods. Especially we are revising our Asian infrared luminosity, X-ray luminosity diagnostic. And in the course of our study, we find the bona fide comptotic AGN with double peak NLRs, and we did some analysis on the torus parameters. And then finally, we are now preparing catalog X-ray source identification in high-pass rim-camera CFHT data set, applying the flux-dependent likelihood ratio technique. Okay, thank you. That's
Thank you very much. So, yeah, there are some questions from Tomogoto. It's number 6. So your third topic. So why one with the K band is the real source?
K band is the real source.
Yeah, why?
Why?
Why one
let's see.
is the real source?
This one. This one.
Yes.
Number 3.
Number 3. Yes.
Okay. Yeah, actually, this circle is a 3 sigma circle, which is a kind of very conservative wide. And if you just look at the image, then it's much closer. It's much closer to the center of the X-ray position. And I don't see no other possible candidates. And if you just look at the image of the X-rays, there are a whole bunch with the kind of K-band excess sources. So it's more likely that the instead of these green ones, this is more likely to be the one. But we can always compare likelihood ratio in K and G, and see the probability.
Well, if it's based on the position, yes, I understand. But the other sources, if you say K-band detection is more likely, then I would say the other sources might be just faint and then not detected in K-band. That doesn't mean they are not X-ray sources.
Doesn't mean, yeah. So my judgment is based on the position. That's
okay. I see.
Position. Yeah,
Okay.
that's three sigma. So
Okay, yeah. There is another question, so please continue discussion on Slack. Thank you very much.
Mhm.